Okay, so usually when we build or design our space transportation system, we look at what is the type of what is going on elsewhere in the world and what is our internal demands for small or medium or heavy launchers. What is the type of usage from the user community? It could be from scientists, it could be from agricultural or from industries. What type of, is it a communication or is it earth observation satellite? And this is how this is a highly dynamically changing situation. Earlier it was like, make heavy launches and then build big satellites. Now there is a trend that you can have many things with the miniaturization of avionics in small satellites. So there are tons of small satellites also in the world. So this is how the that user, the initial the requirements are generated. So we can classify the launch vehicle into, okay, all depends. It's a, we can say Mark 3 is heavy lift. Maybe for SpaceX it could be different. But usually it is like 1 to 500 kilo. If you take to low Earth orbit, it is small. And if it is 8 ton to low Earth orbit, 8 to say 4.5, and again the same way. Like example is our LVM3 or PSLV. And heavy means 10 ton. We take to Leo equivalently 6.5 ton to GTO. And when we modify the Mark 3 with a new propulsion, we are going to enhance it to that level. So it becomes a heavy one. But then there are super heavy like the Saturn or the Elon Musk, that huge vehicle. So this again, we are also working on a design for a super heavy vehicle for the next generation. And if you look at ISRO's fleet of vehicles, this one slide shows the entire thing. We have a small sounding rockets for probing the atmosphere. And then we started the sending satellites to orbit. Sounding rockets, it just goes to 100 or 150 kilometer and it comes back. The payload will come back, and during the descent, you make measurements. But if you want to keep a satellite in orbit, you need high energy. And SLV was that experiment for 40 kg. Then SLV we augmented with these two strap-ons, as you can see here, two solid boosters. These are all solid boosters with 150 kilogram to LEO. But these two vehicles are not there now. Then the next major change in 1993 was PSLV, which can take 1,200 to a geo transfer orbit, and GSLV is there, which can take 2,200 to a GTO orbit, and the LVM3, that is can take 4 ton to GTO. And recently we have added a 500 kg LEO small satellite launch vehicle looking at the world demand, and that is the first flight is over. And the next generation, the huge vehicle like launch vehicle is on the drawing board. Maybe the design will be finalized and it will go through. At the same time, we also take up technology developments. We know that if you want to reduce the cost and also make it a fast turnaround, we need new technologies. One option is reusability. So reusability could be like a aircraft coming and landing. Recently, you may recollect, we have done a landing experiment. And we have test vehicles for proving many of the technologies, like a small vehicle, which can be used for a landing technology demonstration or a crew escape system in-flight demonstration or air breathing propulsion. So it's a multi-purpose vehicle. That vehicle already is realized, and the first flight will be having soon the first flight. Then the RLV, if you want to take to orbit, we are modifying the GSLV like this, and this is again an approved project. Maybe in another couple of years, we'll launch RLV to orbit, a winged body, and then it will be there in space for a few weeks, and then we come back and land in a strip. And then next is air breathing propulsion. That is how we can use air from the atmosphere and then use it for propulsion. So this is another experiment which can. So these are all the experiments or the vehicles right now we are working on. Now, if you look at total, we had 214 missions. Out of that, 57 PSLV. GSLV 15 Mark 3, 6, and SSLV, we had two missions. The first was not fully successful. And there were so many satellites. We have launched 123 satellites, and total 91 launch vehicle missions. And we also launched from 34 countries 424 satellites. And out of that, 15 student satellites. And we did two re-entry missions, that is bringing back an orbiting body to Earth. And there are other activities going on, like inflatable aerodynamics decelerator, how it can be used for decelerating supersonic bodies. So looking at PSLV, it has completed 57 flight, and next July it is going to have the next flight, that is a commercial flight. So this vehicle, though it is called a PSLV, which means Polar Satellite Launch Vehicle, it's a misnomer. This vehicle can take satellite to anywhere, can go to low Earth orbit, polar satellite, or GTO. In fact, it has taken our satellite to Moon and Mars. But so it has got such a flexibility because of the final stage. It has got a last stage, which is a liquid stage. We can be started, restarted. So it's a very main workhorse even today for ISRO. And then we know that after the satellite injection, the satellite is injected, the final stage also goes to the orbit. Usually that stage is passivated and it just circles there. So there is no use. But then we thought of making that final stage, usually as a debris, into an orbiting platform. So that is what we call it as a PSLV orbiting platform, that is POEM. What we do, we just add a little bit of solar panel power, and it has got its own control system. So you can add payloads, and then it can be in space for a few weeks or months, and then it can telemeter data down. We had two POEM missions, and even today, one PS4 is orbiting like a satellite. So it's the first time that a spent stage, which is otherwise called as a debris, is used as a orbiting platform. So GSLV is the vehicle that we started using cryogenic propulsion. You know the history of getting the Russian cryogenic stage, and then initially that we had failures, but subsequently we made our own cryo stage. And we have recently we had a flight where the Indian navigation satellite was launched into space, and this vehicle also is back into action. It has a CUS, which is the cryo stage is called cryo, or the cryo upper stage. And this vehicle has got that strap-ons, that is what you see as around the vehicle. They are all liquid strap-ons. There is a solid stage. Again, there is a liquid stage, and over that the cryo stage. That is how the vehicle is configured. Now LVM3, which is this now as a major vehicle we are developing, and then it has only come out as a continuation flight. Recently, we had two successful missions for OneWeb, 36 satellites in one flight. Like that, we launched two. That is total 72 satellites we have launched for OneWeb for the Gaganyaan mission. And then in July, this vehicle will carry the Chandrayaan. This vehicle has carried Chandrayaan 2. And next July, this July, that is next month, we are going to have fly Chandrayaan 3 using this vehicle, and the vehicle is getting ready. So I was telling this area, small launchers, you can see so many countries are working on small satellite launch vehicle. Even in our country also, startups like Skyroot, and they are all working on small satellite launch vehicle. So that is the need for small satellite. Only we start thought of making a vehicle which is it is a three-stage vehicle. All the three stages are solid stages. So the advantage of solid stage is it is low cost, which can be cast and kept for a long time. Anytime you can take, so that launch turnaround time is less. And it has got a small liquid upper stage for correcting the final velocity correction. Otherwise, it is a all solid stage vehicle having around 2-meter diameter, and it is operational, and we are expecting more launch opportunities through NC. So we also have, as shown here, a fleet of sounding rockets, which we launch, VSSC, we launch every month. Last Wednesday, we launch. We used to have every week, now it is every month. And it's a major attraction for students and public. You can also come, and you can plan your trip and come and witness the launch. So here we have different diameters available, like what is shown on the right side bottom. Rohini sounding rocket 125, 200, 300, 560, depending upon the payload. So the same vehicle we use for many technology demonstration. So this, the RLV, we had a mission, a supersonic mission, again a suborbital flight and a landing mission. And then we are going to have the orbiter mission. And for this scramjet, we had a short duration, that is a few second mission in sounding rocket. Now we are, as you shown here, for a 200-second long duration mission, we are getting ready. We know that reusable launch vehicle in different forms, like winged bodies, are used for many purposes, including strategic application. We recently were at a Chinese vehicle has come and landed after spending months in space. So it's unmanned. Basically, it is used for many applications. So that is, we also started working on it, and it has gone through the development. Finally, the final vehicle, as you see, this is beautiful concept. If you can in futures, if we can configure the lower stage with the wings, we can even think of bringing that stage after its function back and then land on a runway. So these are all possible. Uh, but right now, what we are doing is just a technology demonstration as shown here, where it will be taken to space and then brought back after a few weeks. This scramjet we have demonstrated in a rocket as shown here. Now you can see the shape. These activities are progressing. Maybe another couple of years, we will be launching this scramjet propulsion for an extended duration. That is, it is flying at Mach number 5. Mach number 5 is around 1.5 kilometers per second. You can imagine you can cover maybe Delhi to Trivandrum in few minutes, not in few hours. So this is the configuration and how we are going to use. But this vehicle can be used only during the atmospheric phase, and beyond that, we need to fire the rocket and then take it to the orbit. So another concept we are working on is, can we use inflatable aerodynamic decelerators that we keep in the inflated condition in the vehicle, and then once you reach say one, so for example, once you reach in orbit, can we inflate it and then convert it to a usable volume? It can be a habitat, it can be an inflatable decelerator. So what we do, we have done one test in using the sounding rocket, where it was folded and kept and launched, and then at 80 kilometer we inflated. By that time the vehicle has gone to supersonic condition and inflated, and then while coming down from supersonic to low subsonic, velocity was reduced by the aerodynamic drag. So this is again a concept demonstration. We wanted to see where this can be used in recovering a real launch vehicle stage. So as you are aware, Chandrayaan-1, where we had impacted a probe onto the moon, it was not a controlled, what you call as not a soft landing, but it was very useful in for detecting presence of water there, and again taking our flags to moon. Chandrayaan-2 had an orbiter and a lander, but then you know that lander towards the end we had a failure. Now, learning from the lessons learned from that, we have made the next vehicle, that is Chandrayaan-3. It is now at Shah getting mated with the vehicle, and in July we'll be launching. Then the Astrosat Mars orbiter mission, anyway, you know that. And Aditya is another one which is going to be at the L1 point. We know that L1 point is called as a Lagrangian point in space, where the gravity due to Sun and Earth gets balanced. So if you keep it there, you need less fuel to uh, maintain the orbit of the satellite. So this also will be launched in August using PSLV, and it will travel 1.5 million kilometers from Earth, and it will be looking at Sun and giving very valuable data about Sun and what's its corona and related things. So we have a number of energy systems that we in-house develop. We have silver zinc battery, lithium-ion battery, super capacitor, where we use the capacitor plus battery together, and super capacitor where it's a capacitor and capacitor, the capability is used. Whereas in super capacitor, we just charge it and then fly. So all this energy system, once it matured, many things we transfer to industry. For example, lithium ion we have transferred to an industry and they have produced it. And then such systems through transfer, it will be available to many. So it is maybe very interesting for teachers. How do things stay in space? We know that everything is dynamic. A bicycle, unless it is moving forward, you cannot balance. So it's a dynamic balance. The whole universe is in a dynamic balance. Everything is moving relative to each other. So a satellite at a particular orbit, it is like you have probably would have done if you want to a string, a stone on a string. If you want to make it horizontal, you have to give a minimum velocity. And if the string length is more, you see that the it takes the apparently the velocity is less, but then like that for a given orbit you need a velocity. So this velocity is provided by the launch vehicle. So if that horizontal velocity, again velocity, it has got both magnitude and direction. So the velocity should be tangential to the orbit, then only it can stay. The moment you deflect it downwards, it will be under the gravity and come back. That is how we make bodies to re-enter and then come back. And the advantage of Earth is that it has got an atmosphere to say 100 kilometer, and the huge energy that we are when you take a satellite to orbit, we are pumping in energy to the satellite, and it is having very high velocity, like 7.6 kilometer per second. You just see that's a huge velocity, and for a body like satellite like 1 ton, energy is huge in terms of kinetic energy as well as the potential energy by virtue of its height. So this energy we have to systematically kill, then only we can land. The launching is easier compared to landing or a re-entry and then landing. So what we generally do, the air, we can dissipate the air by aerobraking in Earth's atmosphere. That is the beauty of having an atmosphere. And that atmosphere, that is protecting us from all meteorite and other things or debris that are coming from space. But this is the real problem when we go to Moon or Mars. Moon, there is no atmosphere, so you cannot aerobrake. So you have to carry the propellant and then use rockets that should be fired in the opposite direction to land. So this space capsule recovery experiment was our first experiment in 2007. It was a historic experiment where we have taken a 550 kg satellite to orbit, and it was in orbit for a few days. It has completed microgravity experiment and it has come back. You can see it is the black body with the special tiles, thermal protection tiles, because re-entry due to aerobraking, the heating is very high, and then it has been soft landed with parachute. Finally, as seen here, it was floating with a float, and then it was recovered. So that was, in fact, it was very instrumental for many things like reusable launch vehicle, manned mission like Gaganyaan, how to process microgravity, and how to bring back an orbiting satellite to a precise location on Earth. All these things got demonstrated. So now we are all working on the Gaganyaan. You can see the LVM3 modified like this. You can see in this figure inside this orbital module is the satellite, and it is inside. And this portion is called a crew escape system. And this orbital module has two parts. One is a crew module where crew will be residing, and there is another service module. It is like a satellite. This will give power and all other support during the orbital phase. And once the orbital phase is over, it gets separated, and the yellow portion alone will come back. And it is like this when it is deployed. The solar panel is deployed. Satellites looks like this in orbit. So this is how it is going up using LVM3 from Sriharikota. In case if there is any problem with the vehicle, so you fire the escape system, and then escape system will be fired, and the crew module will be released, and the crew will be rescued. So any stage, if anything goes wrong with the vehicle, you have provision to take out the crew module, release the crew module, and then come and land, so that we always give importance to the safety of the crew rather than the mission success. So this, the different mission aspects, the systems are getting realized. So immediately, maybe in another 1 month or next July or August, we will be demonstrating the in-flight demonstration. As I was telling, this test vehicle will take the crew escape system at the tip. It will take it to some condition, like a transonic condition, and then we release the escape system. So this is how escape systems are tested in flight. because we cannot use a full LVM3 for that. Is very expensive. So you make such low cost single stage vehicle to take it to the initial condition and then demonstrate and prove that yes, escape system will work not only at launch pad but it will work in flight also. So when LVM3 you want to convert LVM3 into a human rated vehicle, it has to go through a process called a human rating. Like you look at the design margins, add more redundancy, and then propulsion stages and all you derate so that you can work at with the higher margin. And then the entire machining and realization process, stringent process control to ensure that there is no mix-up and all non-conformances are either minimum or all addressed well. Above all, it has a vehicle health management system that will collect data from all systems and tell the mission computer that I am healthy or I am not healthy. If I am not healthy, please abort so that the crew's life can be saved. Okay, you are also aware about the space sector reforms going on now in ISRO. Apart from ISRO, there are agencies like InSpace for promoting, hand-holding, and authorizing private space industry. So, if any one of you interested in working in space, you can approach InSpace. NCL is our commercial arm, where we are working on um, the commercial part of all satellites launch vehicles will be done through NCIL, and then there are autonomous bodies as part of it. And then the the purpose of space sector reform is promotion, enabling, authorization, and supervision, so that the ISRO and its expertise is available to all the stakeholders in the country, and many uh, private as well as industries can participate in the program. You can see on the right, that is first sounding rocket already launched by Skyroot from Sriharikota, and there are more startups now. They are all working with ISRO, and probably we hear more as time progresses. If more and more companies will evolve in India also. So examples, so many are there like Dhruva, Skyroot, Bellatrix, Agnikul, Digindra, Satshwar. They're all working for this. And then the Skyroot Aerospace, as I was telling, they are working on Vikram series of launches for taking satellite to orbit and also on sounding rockets. Agnikul, they are working on works with semi-cryo propulsion. In fact, they have tested their engines in VSSC. In fact, we have given avionic packages developed by us for them. So they are all using our expertise and technologies, and they are coming with new vehicles. And at the same time, we should also work on next generation vehicle, where we know that any launch vehicle, it will have associated the products of combustion which are not very good for the environment, like solid propulsion or even a liquid propulsion with the UDMH and N2O4. So it's time that we move to green propulsion. So cryo is a green propulsion because it uses hydrogen and oxygen, and mostly the output will be water. And then similarly, it's another option is a semi-cryo or a liquid using LOX, liquid oxygen and methane, or liquid oxygen and kerosene. These are all options where we can go to green propulsion. And at the same time, the heavy, the booster portion, which is where the cost is more than say 50 or 60% of the total vehicle, after use, can we bring it back, break it, and then properly reservice and reuse so that the cost can be reduced. So this liquid oxygen methane engine, it has to be repaired, restarting and throttling, and we need a cluster of engines. So when the engines are more, so the thermal management and associated thrust level managing, and we are going to have 5-meter class of structures. So it's machining, industry preparedness, as well as transportation of the test vehicle, and using the Gaginian module at the top of it, we can take this capsule to say 100 kilometers. 100 kilometers is known at the edge of space, where the it is called as von Karman line, and we can go there, and then it is just coming back as shown here. So you get around 2 minutes of microgravity flight, and it's a very, compared to Gaganyaan, space tourism is simple. We need to make it more, what you call, it's not astronauts but regular ordinary people only will be traveling. So this concept is there, but definitely it has to be converted into a um, proper say process or a program. Here we are ready to give this technology to industries. They can, anybody interested, they can make, and we can make money, because tourism is not primarily as part of ISRO's activity, but we can always enable those who are interested. I think that is the gist of space transportation system. So I was trying to give you a flyer of what is going on in VSSC. I have not covered India ISRO. I am sure others will talk about you. But whatever we do in VSSC, we all get support, and from all centers, because no individual center can survive. All centers are contributing their own part, and that is how we have satellites, launch vehicles, and all missions like Gaganyaan. So thank you for your attention, and you can take up any questions.